Hello, this is John Pan. I'm a professor at Cal Poly in San Luis Obispo. Today I would like to present the Central Limit Theorem. The Central Limit Theorem is one of most important concepts in statistics. Before we talk about the Central Limit Theorem, I would like to talk about the difference between the population distribution and the sample distribution. So let's assume we have a population distribution in a big circle. We have many different data on it. Let's pick one of the sample. Say this is one sample. If we say S1, the sample 1, within the sample 1, the sample size is n, okay? So we have many different samples. Let's say x11 and x12. The first subscribe 1 means sample 1. We have many different, so in that case we have 1n. So we have sample size of n for the sample 1. From that sample, we could calculate the sample mean x1 dot bar. That x1 dot bar will be equal to x11 plus x12 plus x1n divided by n, right? Now, that is just the one sample. Let's pick another sample. So if we pick another sample from the population, say assume this is sample 2. On the sample 2, assume the sample size is the same, so we could have x21 and x22 and so forth. We have x2n with sample size of n. So in that case, we can calculate the sample mean as well. Let's see, this is x2 dot bar. That will be the same thing. We can write summation I equal to 1 to n, and I think this is a little bit too far. Let's remove that. Okay, so we can see this is x2 dot bar will be equal to summation I equal to 1 to n x2I divided by n. With the same thing, we can create another sample. Say this will be a sample 3, and we could have another sample. Say this will be sample 4, S4, and so forth. We can calculate x3 dot bar, x4 dot bar. Now, with all those numbers, the x1 dot bar, x2 dot bar, then we could have x3 dot bar, and many, those sample mean, those are the statistics. So those statistics, they have their distribution that called sample distribution of a statistic. Now, the statistics could be a sample mean, which is x bar, and the statistic could be the S, which is sample standard deviation, or could be the sample proportion. So the central limit theorem is talk about the sample distribution of a statistics. Mainly we talk about sample distribution of a sample mean. So the population distribution describe the individual. This is individual, which is, if I see, this is individual X. So the population distribution is to talk about the distribution of X. A sample distribution is describe how a statistics, and so one of the statistics will be, if I change the color, could be the X bar. Okay, so the distribution of X bar is a sample distribution. So what the central limit theorem talk about, let x1, x2, and xn be a random sample from a population with the mean and the mean mu and the variance sigma square. Now this population could be any population, okay, any population, as long as the population has a mean mu and the variance x bar. We can calculate x bar, which is equal to x1 plus x2 plus xn, be a sample mean. That sample mean, if the sample size is large enough, in the most cases we see the sample size is greater than 30, the sample mean will be approximately normally distributed, that the mean of the sample mean will be equal to the mean of the population, which is mu. The variance of the sample mean will be equal to sigma square over n. If we use Sn to calculate the sum of the sample, the sum Sn will be approximately normal as well, with mean equal to n mu, and the variance will be n sigma square. The central limit theorem does not require a population follow any of the distribution. So it's no matter what population distribution is, where the sample was drawn from. So how can we to prove that central limit theorem? To prove central limit theorem in theoretical is very challenging. However, we can use simulation to prove that.